Energy Society's 2020 conference being held virtually originally from Washington, D.C., but now via the internet projected all around the world. You are joining us here for the technical track where we will cover both all three areas of photovoltaics, thermal energy, and energy storage. We are featuring a panel of 7 top-notch speakers from all around the world. They will each be giving vignette presentations. We have pioneers to the industry as well as new and rising stars. So thank you very much, everyone. The speakers' topics will be covering the speakers' talks will be covering topics that are diverse but also very focused. We cover utility scale applications. We cover post-COVID permitting platforms and performance optimization of residential PV systems, solar thermal and geothermal storage applications for the heating and cooling of buildings in all climates, and then stress management for high temperature energy storage design. We've attempted to organize the 7 speakers to start with materials and then go to buildings and then go to systems. So today for our first speaker, I'm happy to introduce Zhenzhen, who will be talking about storage material design. Zhenzhen, please take control of the screen.
Okay.
Thank you.
So you should be seeing my screen right now, right?
We are.
Okay, great. So today I'm gonna present our recent work on the cracking risk mitigation in the molten salt 347H stainless steel hot tank wells. And this is a collaboration between Colorado School of Mines and National Renewable Energy Laboratory in Golden, Colorado. Okay, so first of all, we have studied the literature and find that there have been more than 50 reheat cracking related issues in the austenitic steels that is designed for the high temperature working environment. So the materials include 347H stainless steel and 316H stainless steel. And majority of those failures is related to the weldment that did not experience post-weld heat treatment process. Okay. So, and also there are some reported cracking issues in the heat affected zone of the thick plates welded thick plates, and also for high temperature service conditions. And a list of stainless steel materials is listed, for example, 347 and other typical stainless steels. Okay, so let me enable my laser pointer. Okay, all right, and we also noticed that the TNO reported reheated cracking failures in other alloys like nickel-based superalloys. A lot of them are listed in here, okay? And then the majority of those materials that has reported issues are precipitation strengthened, meaning they have certain precipitates distributed in the microstructure to make the material stronger, okay? So, and the particular material that we are working on is the 347H stainless steel. Okay, and our industrial collaborator informed us that there are cracks observed in the floor wells of those thermal storage hot tanks in the 2nd generation CSP system. Okay, and then the filler material that they were using is 347H as well. Okay. And then the maximum service temperature is 565 degrees Celsius, and the thickness is about 2 inch. Okay, so first of all, let's see what is the composition of this stainless steel. So in addition to those typical compositions that you would see in other materials, okay, we find that the add intentionally niobium and nitride, okay? And the reason is to form niobium nitrides instead of forming chromium carbides. So this composition, if this form, it will typically take out of those corrosion resistant element chromium. And then that will cause a well-known problem called stress corrosion cracking, okay? So instead of forming this by adding niobium and nitrogen in there, so you can form niobium carbon nitrides that will also serve as a precipitate that strengthens the material at the moderate elevated temperature between 590 and 650. Okay, so but by adding this niobium carbon nitride in there, it has some problems associated with it. So for example, during welding, in the partially melted zone that is immediately adjacent to the fusion zone, you will have the a liquid film forming. Okay, so those white features in there, that is typically the niobium carbon nitride eutectic phase that has a lower melting temperature than the base material, and that will form a liquid film, and that is cause the cracking issue. Okay, and another mechanism in this material for cracking is ductility dip cracking that is related to the grain boundary creep, accumulation of strain into the regions near the grain boundaries and causing the earlier cracking. Okay, and then this image here shows a typical fracture surface. Okay, so you can see all the grain morphology. So that means it's cracking along the grain boundaries. Okay, and today we're going to focus on the cracking mechanism called reheat cracking or stress relaxation cracking. That is known to be the cause for the cracking issue that is being observed in this floor welds. Okay, so first of all, we have to have residual stress. That is number one factor leads to the cracking issue. Okay, so this shows a simulation results the residual stress distribution after welding, and this center red region shows where the weld pass is. So you would expect a high tensile residual stress remaining in the material after welding process. Okay, and then when you put the material in the high service temperature, so for example 600 degrees Celsius in this case, by doing the simulation, we can see this is the transformation temperature for the niobium carbon nitrides to form. So apparently, if you put the material at this service temperature, the niobium carbon nitrides will start to form. And then when they form, they would like to preferentially form along the grain boundaries with some coarsened precipitates, and some of them will form within the grains. Okay, so this is at a scale of roughly a few microns. Okay, so and then when you have the residual stress that starts to relax at this elevated temperature, they will preferentially go into those dark regions that does not have precipitate to strengthen them. Okay, so because this is a relatively soft region. And then when you have sufficient of stress relax into this region, you will start to form all those cavities. Okay, and then eventually you will see cracks forming in this region. So that's the mechanism for stress relaxation cracking. So that's why in our test, we want to duplicate the weld first and then test the susceptibility of this weld to the cracking. Okay, so first we made in the lab this setup. Okay, so and you see this is where the 2-inch thick steel plates is being clamped on, and then we have the single V groove to deposit the welds, and this is all designed based upon the inputs from our industrial collaborator, which is simulating the real industrial environment fabrication procedure. Okay, so this is showing how the weld looks like. Okay, and we also create finite element simulation trying to simulate this welding process. Okay, so those two images shows the residual stress distribution after welding. Okay, and we also have the how much of deformation is being introduced into the material because of welding. And this one shows we simulated the thermal history during welding process and see how the microstructure looks like. So you can see all those liquid films is start to form, wetting the grain boundaries. Okay, and then we use the Global machine cut, which is a thermomechanical simulation tool. So we simulate the stress and we simulate this temperature, and we want to see the susceptibility of the materials. So before the stress is being applied, you can see the microstructure, the starting microstructure after welding. Okay, and this is the fracture surface that we see when the sample failed. We can see the intergranular cracking that shows all the grain morphologies. So this is what we got so far, the susceptibility result. Okay, so you can see at different amount of pre-deformation and also at different testing temperatures, you can see how much time it takes for the samples to fail. Okay, so and then even for the sample that did not fail at this point, you can see the cavity is already forming along the grain boundaries. So if we give it a longer time, it should fail eventually, okay? So this tells us if you don't do post-weld heat treatment, eventually at all sorts of temperatures, you're gonna experience either a short life or longer time of the component that eventually will fail, okay? So that's why we really need to provide a mitigation solution to help to mitigate this cracking susceptibility that we are expecting to occur in those 347 stainless steel thick welds, okay? So there are two solutions. First is we can run a two-step post-weld heat treatment, because if you do only one step, eventually at whatever temperature that you put it under, it will crack, just a matter of time, okay? So we run this two-step post-weld heat treatment. So first step to relieve the stress, and second step, we want to stabilize the niobium carbon nitrides. So it will not form those preferential coarse carbides at the grain boundaries and then fine carbides in the inside of the grains, okay? And for future tanks, we would evaluate other materials instead of 347 stainless steel. We will try a 316L. This is a new grade that has extremely low carbon concentration that was originally developed for nuclear applications. So we think this might have a less crack susceptibility. And we will also recommend to replace the filler from the original 347H filler to the E16.8.2 filler that has a lower susceptibility as well. Okay, so this project is being sponsored by DOE and NREL, okay, and we also have support from Lincoln Electric, Qiuhua, and also Brahman for the welding procedure. Okay, thank you. Any questions?
Thank you, Zhenzhen. We have another minute or two. We may need to ask Ahmad's help. We have now 30 attendees. I know some people may have joined after we got started, but welcome all. If there are any, I don't see any open Q&As at the moment. We can wait, and here comes one. And Ash, you will be next, so I know you're getting queued up. Paul Henshaw.
Unshare the screen.
Yes.
Okay.
Shen, Paul Henshaw has got a question in the Q&A about the molten salts directly contacting the steel. Is there an effect of this? Any effect on molten salts directly contacting the steel?
The reason that we use 347 stainless steel is because it's corrosion resistance. So there's no concern of the too much of corrosion attack to the material. I mean, that's this 347. The reason to use that is because, first of all, you avoid the formation of chromium carbides that is a known source for pitting to start. So, so we should be able to control the corrosion life by using this material.
Thank you. Shen, you can see the Q&A. There's some more coming in. I want to keep everything moving, but thank you. Really awesome presentation. With that, I would like to introduce Ash, who will be talking to us on glass material performance in buildings. Ash, please share your screen and let's get underway.
Okay.
Thank you. I'm just going to stop the video here for a second and then share, because I'd like to. Can everybody see it?
We can.
Okay, so welcome. I'm Dr. Ash Ragheb, an associate professor of architectural technology at Lawrence Technological University in Southfield, Michigan. And today I'm going to talk about dust problems on PV modules in the US climate zones. This is not, I didn't author this. This must be an elephant finger or something to have this big. The study objectives, just to providing an overview on PV soiling problems, especially dust and sand or combination of both, review the impact of the dust deposition on the performance of the solar PV, and looking at some of the future area. And most importantly, I have compiled a nice table. It's very crowded, but you can read it in the paper regarding reduction recommendation for each of the United States climatic zone. And for this reason, I used ASHRAE, that's American Society of Refrigerating Air Conditioning Engineers. This is like our Bible that we use for building codes, especially energy codes and stuff. So there's some other classifications, but I would rather go with my my Bible that I understand rather than something very complicated like Koppen, Geiger classification or whatever. So I'm gonna show very quick the previous research. I don't intend to spend more time, so we'll spend more time on the climatic zone. So two directions of research in this topic. The first one is wind effect direction, exposure time. These studies looked at the system characteristics such as the tilt angle, glazing types, and its impact on dust accumulation. The second are more sort of a comprehensive studies on dust particles, physics, and chemistry with some experimental findings here. This study examined the reduction of transmittance versus tilt angle in the Arabian Desert. So they found that, okay, the more you go with the tilt angle this way, you get the transmission reduction comes very minimum, which means that at 0 here at the beginning of the spectrum, you have a dead flat module that reduce even up to, this is 64% of the efficiency of the PV module. And funny things here that you can get in 3 days only with a 0 tilt, you can get 30% in reduction right away. Again, this is like a trade-off between the tilt angle and the dust accumulation. But anyway, so that's the same thing. This study investigated the physical properties of the dust accumulation and the position density and their impact, of course, on the degrading PV efficiency. It shows this used sort of an artificial dust with different dust types, as you see here. Limestone, carbon cement, and limestone, of course, of different sizes in microns, 50, 60, and 80. So this study revealed that the impact of cement particles to be most significant. The carbon, which is in here, this is my first graph here. This has the most deteriorating effect because of they are very tiny and greatly affect the PV efficiency in just no time. So again, finer particles, when you go coarser, as these curves are, the dust deposition intensity increases, but it takes time, and wind can blow it right away. Easily. So the problem is the finer dust. This one was done in Kenya, and they looked at different intensities here, as you see, 700, 600, 500. So with higher intensity, they found that the reduction output of the versus the thickness of the dust was minimum. But as you see here, when you go down to 400 watt per meter square, and sorry here I'm metric, the loss was like near 25% with lower intensities. This one here, this is another study experienced or experimented 10 glass plates with different tilt and azimuth angles. The glass transmittance was evaluated at regular intervals over a 7-month period of prevalent wind conditions. And they found that a reduction in dust deposition from 15 or 16% for zero tilt to 4.4 with a 90% tilt angle here. So they suggested weekly cleaning cycles as a recommendation to account for this reduction or this tilt angle. The final one here, this has been done in the, I think one of the Arabian deserts, and they looked at the particle size, and they found that a particle between 15 and 25 has the most deposition on the PV here, and consequently the lowest efficiency of the PV. So let me jump to my interesting part here. So this is US climatic zones, again by ASHRAE. It's divided into, it's from 0 to 8, but we don't have 0 here. So we start with 1 all the way in Miami-Dade County, which is, it does have a designation of 1 and another letter. So 1 is very hot, as you see here. 2 is hot. 3 is warm. 4 is mixed. 5 is cool. 6 cold. 7 very cold. 8, which is probably in the second one here, that's in Alaska. That's Arctic, cold, and then the designation letters, as you will see from the next slide. So if you look here very carefully, you will see that this line here divides the United States into moist on the right and dry on the left, except, as you see here, just I would say like 100 to 200 miles off the coast of the Pacific, which is we call marine very heavy rains. This is even more classification on each zone, which I suggested some mitigation recommendation for the dust by each zone. As you see here, again, this line just divides the zone. So the zone here has same color as you see, but once you move here, this change color, this the zone 4 here changes color, zone 2 changes color due to the dry and wet. So this is the precipitation, and why I brought this, because it helps tremendously in cleaning or self-cleaning the PV. This line here, again, the line that I talked about, divide the US, and this line as well on the Pacific Northwest and West. So what I did here is simply I got the climate zone here. A means moist, B means dry. So so A here, that's Miami-Dade County, Florida Keys. These are mostly low latitudes. So they have good efficiency, like the studies that have been done in Kenya, but the dust is kind of a problem, although that's not severe like the desert problems here. So it the constant rains just clean and minimize the dust accumulation. When we go up a little bit with the hot humid 2A and 2B, these are the area in southern Georgia, Alabama, Mississippi, southern Texas. These are still mostly low latitudes, but they utilize wind sometimes during dry season to blow dust away from the panel. Bottom line, you have to clean this. I'm not going to go into every nuts and bolt in here, but you can read this from the paper. But the cleaning mechanism here, it goes from a week, weekly, sometimes daily. If you have a dust storm in Arizona, New Mexico, Nevada desert, you have to clean this, and I'm going to show you some cleaning devices here that are used widely in these regions. But the cleaning periods go from 1 week all the way to up to a month in, let's say, the 4C, this region here. I don't know why these west region, zone 4. You don't have that much of a problem here in the east when you go up, because when you go up here, tilt goes up as well, which again minimize the dust. So the only problem here might be some of the desert, like Colorado and some higher latitude, high latitudes. These require high tilt angle, but you can have sun movable tracking. Sometimes may be needed to harness the solar at this regions. This is the recommendation in 3 points: areas with low soiling condition and or periodic rain, like Northwest. Dust prevent no major problems. Naturally, rain, snow would clean the surface periodically. This is valid in the most wet or moist areas in the United States. Areas of high moisture, this comes as well with some morning dews that kind of make a compound with the dust. This needs the cleaning in these areas. Otherwise, rain and snow will take care of the problem of soiling or dusting in these areas. This is why we're simply cleaning to avoid this compounding of dust and water. Desert area, Southwest, Eastern California, you have to clean regularly. Wiping, cleaning robots, or protective glass coating has to be used in such areas. These are some of the mechanisms here. It ranges from manual wash to accessible. So the picture here on the right, this is an accessible PV modules. This guy is cleaning on the left here, probably zone 6, 7, and 8, accumulated snow. You have a machine and robots for more areas, less tilt. So these, the lower right here is probably a zone 1, 2, where you have like low tilts. You have here a sprayer. Here you can have a sprayer that can clean in dry zone 2B, 3B of the climatic United States. This is more machine and robots. You can have these machine on the lower left here. In conclusion, a paper presented the research development challenges relating to the dust deposition, provided some analysis on the environmental effect, dust deposition, chemistry, properties of dust particles, analyzed the United States climate zone to provide dust mitigation recommendation based on the variation of each weather zone, and highlight the problem with especially associated with desert climate in regions in the southwest of the United States, or mainly dry regions. Thank you so much.
Thank you, Ash. Dr. Ashraf Ragheb from Lawrence Technical University in Detroit. There are a few questions that have popped up, Ash, that I'm going to have you respond to on the chat, the Q&A chat. I notice Zhenzhen, thank you. You've responded to some of the comments. I think, I'm not sure, but let's keep the dialogue going there as we get to the next speaker. For those that weren't here for the beginning, I think you all know where you are. It's in the technical track for PV, thermal, and storage. We have 7 speakers. So far, we've heard from Zhenzhen Yu from the Colorado School of Mines on cracking risk mitigation in solar salt 347H stainless steel welding. We've also just heard from Dr. Ashraf Ragheb on the self-cleaning glass and recommendations for PV system performance. Next, we have Qiuhua Duan from Penn State University, who will share with us her research on estimated hourly insulation for sustainable building design. Qiuhua, please take over the screen.
So
Great,
you
thank
see
you.
my screen right now?
We can.
Okay, thank you. Hello, everyone. Thank you for attending this session. It's my honor to be here today. My topic is estimating the hourly solar NIR irradiance for sustainable building engineering. So here is my outline for my presentation. I will start with introduction. As we know that the solar radiation is a key fact influencing a sustainable building engineering according to both optical and thermal properties of building envelopes. Solar irradiance data in a conventional weather data files are usually broadband, mainly include the three components: ultraviolet UV, and visible light VIS, and the near infrared radiation NIR. However, these three components play different roles in solar architecture design. For instance, solar visible light usually benefit to indoor building energy saving. For example, the electrical lighting, while solar NIR is beneficial to building energy saving in winter, but undesirable in summer. So therefore, there is a need for reliable separate analysis focusing on individual solar radiation components. However, the traditional or conventional meteorological data in weather files do not normally include the spectrum power distribution data of incident solar light, because measuring spectral solar irradiation is much difficult and expensive than measuring broadband radiation. To address this research gap and the practical need for solar architecture design, this week in this work, in this study, we have developed an estimation model for NIR component that can be captured efficiently from reality available data set without additional new measurements and associated sensor, just using existing meteorological data file. Then this can be convenient implemented into current solar architecture design and research. So in this work, two major data sets, including meteorological measurement TMY3 and outdoor solar spectrum data weather, was selected from the database of NREL Solar Radiation Research Laboratory. Data period is from January 1st, 2018 to December 31st, 2019. Time period is from 7 a.m. to 8 p.m. The TMY3 dataset was used to retrieve and process the independent or predictor variables, including GHI, global horizontal irradiation, DNI, direct normal irradiation, and DHI, diffuse horizontal irradiation, and some cloud coverage, dry bulb temperature, dew point temperature, relative humidity, pressure, wind speed. And we also used outdoor solar spectrum data weather to calculate the main component of the dependent variable NIR. During the data process, we calculate the fraction of NIR over GHI as a dependent variable. In order to potentially enhance modeling accuracy, we also generate 2 additional predictor variables, including clearness index KT and cloud transmittance TCLD. These are their equations for calculate these 2 additional variables. All these variables include the fact it's related to the, we can find them in the available existing weather data set. So in this study, we used RPart package in R software to build regression trees for NIR over GHI. We slip the data set, the entire data set into a training data set and a test data set. The RPart implication, the RPart package first fit a fully ground tree onto the training data set. And then it proved fully grown tree by k-fold cross validation and default k equals to 10. In this figure, we can see this cross validation arrow plot for the NIR over GHI tree model. And then we based 2 rows. First is minimum X arrow. So from this figure, we can see when CP equals 0.01, the size 10 of the tree, of the model tree has the minimum cross validation arrow. So this tree is shown in figure 2. The second row, we use the 1 standard arrow or 1 dash SE arrow. In this figure, we can see red, this red dashed line means the 1 dash SE row. So this means we're in under this line is the minimum X arrow plus X standard arrow. This proved regression tree model is shown in figure 3. From figure 2, we can see that using this classification, we can get a tree containing 10 terminal nodes for NIR over GHI. So these 3 groups, each group has include some data with the mean value. For example, this group has 16.7% of the data, and with the mean value is 0.391. And this group has 33.5% of data, and the mean value is 0.414. So these 3 groups include most data. And this tree model, the most important variables, including KTRH, KT is clearness index, and RH is humidity, relative humidity, and dry is dry ball temperature, and dew point temperature, and DHI is direct horizontal irradiance, and T cloud is transmittance, the cloud transmittance. So from this figure is proved the regression tree model. We can see the cut procedure just gave us 3 terminal nodes. and they include all the data. They just have three groups. We name these two model as in figure 2. We name this model as model 1, and this model named as model 2. So in order to further understand each model's estimation performance, we calculated the root mean square error. In short, is RMSE, and the mean absolute error, MAE, of these two models on the test data set. And from this table 1, we compare the RMSE and MAE of these two models. And we can see, we can find the accuracy level difference among the models when legible in this work. Both model 1 and 2 had excellent prediction performance for NIR over GHI. This offers the opportunity to simplify computation process if the weather data are insufficient. So last, I will land on the conclusion and future work. In conclusion, this work demonstrates the feasibility and excellent prediction performance of regression tree models for hourly NIR over GHI. The solar spectrum and conventional hourly TMY3 weather data obtained from the NREL solar radiation research laboratory can be used for model development. And this research also provides a statistical method to convert broadband solar irradiance data in weather files into NIR solar component for building energy and performance related studies. So in the future, we also want to study the effects of the other atmospheric parameters on NIR components. And we also want to use the similar method to model a visible light component based on a conventional weather data set. We also want to figure out more method or other statistical modeling for visible light and NIR components. Our research is supported by the NSF, award and this career project funding. So that's all I have today. Thank you. Any questions?
Thank you very much, Qiuhua.
Mm-hmm.
And I know your professor, one of your colleagues, has joined here. So what we're doing is to keep the conference flowing, we are channeling all questions to the Q&A platform at the bottom of your screen. And Zhenzhen and Dr. Ashraf have been able to respond to a few there, but other folks, please keep the questions coming in there. And again, we've got folks coming and going on the attendee side. We are in the technical track, PV thermal and storage for ACES 2020. We've already heard from Zhenzhen Yu from the Colorado School of Mines on cracking risk mitigation for welding design in stainless steel. Dr. Ashraf Ragheb at Lawrence Technical University on self-cleaning glass materials for PV performance. We've just heard from Qiuhua, and now Gaylord Olson is going to present to us on new ways to combine solar thermal with geothermal multi-source heat pump performance and design. Bennett, are you able to share Gaylord's presentation?
Yes, give me just 1 second.
Thank you. Hello, Gaylord. How is your speaker working?
Well, I can hear everybody. Can you hear me?
We can. That's
All
great.
So,
Bennett will be loading your screen, your information up here momentarily.
okay. if his doesn't work, I could try it again, but I'll wait and see.
No,
We
Bennett's
are.
got it. Bennett's
Yeah,
the guy.
great. And so, all right, the opening screen is here, and we can just move right along to the very next one. Sure, right there. I'll let you all read this. I'm going to move along pretty quickly, but basically, I'm working with a few other engineers on what would be called multi-source heat pump concepts. And it looks pretty promising. And this would be kind of an offshoot of ground source heat pumps, but it would combine either solar thermal or an air to liquid heat exchanger, sometimes called a dry cooler. Lumping these two or three things together gives some significant advantage, we believe. And that's in the bottom line here. The ground loop for a ground source heat pump system is often the most expensive part of the whole thing. And so we think that based on some research and studies in Europe, the size of that can be reduced at least in half and maybe 60% lower. But at the same time, the system would have a higher efficiency, which means lower electricity use. So it's kind of a win-win proposition if it works out like we think it should. I'm going to try to move right along here. Go on to the next one now. There we go. I know you can't read all of this, but you can read it later after the presentation is posted online. But all I'm trying to do here is bring out some research from people in Spain. And they actually built and tested this dual source heat pump concept. And it works fine. They get, as you can read in the fine print near the bottom, they have a ground source heat exchanger size, which is half of the normal size needed for a conventional system. So that's the main point we're trying to point out in this abstract of the paper. Half-size ground loop. Move on to the next slide. All right, this is what they do. This is a very simplified block diagram of this dual source heat pump. They've got an air to refrigerant heat exchanger at the top. They've got a ground heat exchanger at the bottom left. And they put everything in one single box. And they have domestic hot water, DHW, out of this box. And they've got user space conditioning, that is heating and cooling for a building at the bottom right. So anyway, that's what they do, everything in one box. Moving to the next slide. This is a system from Germany, and this is actually what we think is the first multi-source heat pump system available for purchase anywhere in the world, perhaps. And you can see the headline there. They claim to have the most efficient heat pump in the world. And I'm not sure if anybody's challenged them on that, but it may be true. And as you see down near the middle, it says they have 2 regenerative heat sources. And actually, they've done a little bit better than that, as shows up in the next slide. This slide is kind of an artist pictorial of a house that has one of the ThermSelect systems. ThermSelect is the name of the company that originated the product. And here they're showing actually 3 different sources. They have solar thermal collectors on the roof. And they've got an air to refrigerant heat exchanger off on the right, which is number 4. They've got a ground loop, number 5, which could be vertical or horizontal. And they've got 2 other units as part of the system. The number 1 is the main heat pump box inside of the building. And the number 2 is a user interface and control box to make the system all tied together. So in contrast to the system in Spain, where everything was in one box, that's not the case here with this German product. Move along to the next slide. This is a sister company, also in Germany, and they list a few bullet points giving some of the benefits of this therm select system. And as you can read there, the second bullet point says they're going to reduce the source development cost because the brine collector or the bore, that's the ground loop size, only needs to be dimensioned half the size. So we have two different systems, both from Europe, that show about a half size ground loop, which saves a lot of money. Go on to the next slide. Okay, this is a total solar assisted heat pump system from people in Italy. So now we've covered 3 countries. We got something from Spain, from Germany, and now from Italy. And I won't bother dwelling on this. You can read it later if you want to, but go on to the next slide. The next slide shows the operating modes for this system designed by people in Italy. They designed it only for cold climate parts of the world. And you can see that at the operating mode 1, they have the solar heat feeding into a buffer tank, and the water from that tank feeds into a water source heat pump, and from there into the building. So that's the straightforward solar heated building concept. If the sun doesn't shine, you go on to mode number 2, and the building still gets plenty of heat, but it has to come from the ground loop. It goes to the tank and then to the heat pump into the building. In the summertime, when the building does not need any heating, the solar collector feeds hot water into the ground loop to warm up the ground all around that loop. So they're trying to make the ground as warm as possible for the upcoming winter. On to the next slide. This shows the 6 different parts of the world that this system was designed for. And I know you can't read this very easily, but I picked out the worst case of these 6, which happens to be the upper left example, which is a city in northern Poland. And that's zoomed in on the next slide. So move on to the next one. So as you can see here, if they have nothing but a ground source heat pump design, which is pretty conventional, then you have the solid line. So the ground loop gets colder and colder every year, which means that the efficiency, in this case, they're showing it as COP, coefficient of performance, it gets worse every year, which means electricity bills will be higher every year. It'll eventually stabilize, but probably after 15 years or so. If they add the solar thermal into the system, everything is much better. Instead of the ground getting colder every year, the ground is actually getting warmer every year. So if you look at the green triangles or the X's, those would be the logical choices, because there, in the case of the green triangles, the size of the ground loop is reduced in half. 20 boreholes, 10 boreholes instead of 20. So now we have 3 examples from 3 different countries where there's a way to reduce the ground loop size by a factor of 2. Now moving on to the next slide, there's a much different concept which comes from people in Belgium. Can we get to the next one? Oh, there we go. Yeah, again, this is just the front, the cover page for this article by 3 people in Belgium. And again, this is the 4th example where they say that there's a reduction of 47% in the bore field size. And so this is pretty consistent. This is a big reduction and a big savings of initial cost for the system. Now, the people in Belgium have a much different approach, as shown on the next slide. They don't have an air source mode. That is, in this case, they have a dry cooler, which is simply an air to liquid heat exchanger. And the dry cooler does nothing more than precondition either of 2 ground loop regions, a warm region on the left and a cold region on the right. So this block diagram shows the case in the middle of the summer, a hot summer afternoon. They're getting nice cold water from the right-hand bore field And at the same time, with a separate water pump, they're doing preconditioning with hot water from the dry cooler into the other ground loop. And so in the opposite season, which is the next slide, in the middle of the winter, the coldest winter night, they're getting nice warm water from the left-hand ground loop to feed into the heat pump and into the building. But at the same time, the dry cooler feeds very cold water into the other bore field to precondition it for the upcoming summer. So we'd like to combine all of these techniques that have been shown so far. And go to the next slide. And we think there is a way to do that. So on the left-hand side would be the cases for examples from Spain and Germany. They can choose an air source mode or a ground source mode, but they don't have any preconditioning. The one on the right does not have an air source mode. They have a dry cooler, but it's not feeding into the heat pump. It's only preconditioning 2 separate regions underground. But that also gets a 50% reduction in the ground loop size. So ideally, we'd like to combine both of these methods and put them to use. We expect that there would be a greater than 50% reduction in the ground loop size by having both techniques at the same time. And we believe there's a way to do that, which is in the next slide. So this is one way that we believe would be a fairly straightforward way to accomplish what we're aiming at. The system has 3 water pumps, as shown by the triangles and the circles there. Those are simple water pumps. The top one is going to be required in any case because the heat pump has a source fluid that always has to have a pump. So all we're doing is we're adding 1 additional water pump, and then there are 3 water valves, as shown by the triangle symbols there. These are 3-way valves, and they have 4 different settings. So moving on to the next slide. The next slide shows the way these valves can be set to accomplish what we want to do. These 2 examples show the same thing that was accomplished by the people in Belgium with their paper. As you see, there are 2 separate ground loops, and we can precondition one while we use the other one. The coldest winter night on the left, hottest summer day on the right. There are many other modes which show up on, yeah, let's go to the next slide. Okay, this shows what we call a parallel mode, where you can actually simultaneously have water coming from one of the ground loops, but at the same time, part of the flow comes from the above ground thermal exchange unit. Now that above ground thermal exchange unit could be a solar thermal collector. And as a matter of fact, if you have an unglazed solar thermal collector, it's useful for both hot and cold in the same way that a dry cooler is used as a heat exchanger. So that's why it has this long terminology there, because it can be solar thermal or it can be an air to liquid heat exchanger. So now this parallel mode has a benefit in the transition region, showing on the next slide.
And
Yeah,
Gaylord, if we can, we have to move it along here a little bit. We're starting to run out of time.
This is pretty much my last one. And so the rest of the slides just show some specific examples going a little bit beyond where we are. So I can stop right there, and we can move right along.
I'll take you up on that, Gaylord. Really fascinating information all around, but I know we're down to 31 minutes and we have 3 speakers left.
Yeah.
So there are questions coming in on both the Q&A and on the chat. We are over 50 participants in this session, so yay for ACES. Really glad to hear that. And without ado, there we go. Jeff Cook, Dr. Jeff from NREL with a really timely topic, SolarAPP. Please launch right into it.
Thanks so much. And I think you're actually seeing probably the presenter mode. So I'm going to switch and share a different screen real quick. So bear with me while I do that. And now you should be seeing a full screen of the presentation. Is that what you're seeing?
Yes.
Great.
Yes, we are.
All right, thanks so much for the time. Really excited to present here at ACES. So like Tom suggested, we're working here at the lab a project around automating permitting for residential rooftop solar. We started this project back in September of this year, having no idea that we would be where we are today. And so the idea of having an instant online approval process for solar permitting has become even more important in the no-touch permitting world we find ourselves in given COVID today. So really excited to talk through the work that we're doing here at the lab in this space. Why we started this work to begin with really relates back to the fact that residential PV markets are rapidly expanding across the country. As many of you may know, back in 2015, we reached 1 million PV systems installed, and that was a really big deal. We now doubled that over the course of 3 years, and we're going to continue to see the market increase, which is great for a lot of reasons and supports a lot of local government's goals. A lot of folks have renewable energy commitments, 100% clean energy goals. They also have interest in economic development that solar installations and contracting can provide in their jurisdiction. And there's a lot of positives to solar deployment in those spaces, including improving emissions levels in a jurisdiction. But there are some issues with more solar projects, and that is that there are a lot of more permits that need to be approved and inspected than there were before. And jurisdictions don't necessarily have more staff to meet the growing workload. So one of the goals of the lab is to try and streamline permitting, inspection, and interconnection more broadly, PII. But today, we're really talking about the SolarAPP software. But I did want to make you aware of the broader agenda here that the lab has in looking at permitting, inspection, and interconnection as a package of activities that occur sequentially or in parallel in some cases. So as you can see here right now, NREL is doing two things. I'm going to talk about the automated permit processing platform in more detail today and why and what that looks like. But we are also doing analysis around permitting, inspection, and interconnection to offer a couple of things. One, we're trying to identify the variation in permitting requirements, inspection, and interconnection requirements across the country, to identify how those requirements vary, how they relate to overall cycle times, how long it takes to get from permit submitted through permission to operate of a residential PV system, and then also how that relates to cancellation rates. So if you have to wait longer to get a permit, are end-use customers more likely to cancel because they had to wait? We're also going to be correlating those things with deployment in jurisdictions and ultimately developing a mapping tool that'll be available by September of this year. And that mapping tool will identify how, peer city A and peer city B that look a lot like each other on all characteristics. For example, they may have the same utility, they may be in the same state, but they might have wildly different permitting requirements, wildly different cycle times in terms of and wildly different levels of deployment. And so we're going to have that mapping tool so anyone can go in and check and see how their jurisdiction or utility is performing in relation to others, and that can be an opportunity to align with best practices. And for permitting jurisdictions, AHJs, local governments, to consider perhaps adopting the SolarAPP to help streamline their permitting processes, because the SolarAPP offers instantly approved projects that are where the software is doing the plan set reviews to ensure that the system as inputted into the application would align with model codes, those model codes being the 2017 National Electrical Code, the 2018 International Residential Building Code, and then the 2018 International Building Code. And so we took those model requirements, we integrated them into the SolarAPP in the past 6 months. We've been vetting those requirements with jurisdictions and code officials and state and contractors, and we've now integrated it all within the SolarAPP. If you want to learn more about the SolarAPP, you can go to our website, solarapp.nrel.gov, and see where we are and be able to follow along with the work. But right now, we're testing and piloting the SolarAPP with jurisdictions, and we're actively looking to work with more jurisdictions to get them this tool as soon as possible. Ultimately, you can see we're in the piloting phase. We're going to launch the tool for widespread use. It's the end of our fiscal year, which is in September. And then we'll be working over the next year with a long-term program manager. So NREL right now has a source of thought notice out, looking for interested organizations to take this platform from the lab and deploy it in the market. And so we'll be selecting that long-term program manager in the coming year to work with them to transition the platform into 2021 and beyond. So that's a roadmap of where we are. I wanted to flag for a bit more on the testing and piloting phase. So right now we are working with 3 jurisdictions on the testing process, all of which are from California. And so right now what we're doing is side-by-side comparisons of, we have the contractor submit their typical, the traditional plan set that they would send into a jurisdiction, in addition to the SolarAPP approval documents. And so then the jurisdictions review both documents and what the SolarAPP is saying, and then they can approve or make corrections on the SolarAPP and help us improve the application process. So we're actively doing that with 3 jurisdictions, as I said, in California. We're looking to expand that market beyond into the next 3 months to include other jurisdictions from other states, including we're interested in states and jurisdictions within states in Colorado, Illinois, New Jersey, Florida, Maryland as a couple of examples. So we're actively considering all sorts of individuals. We're developing a survey to help develop a SolarAPP local government interest survey to help queue up the piloting cities, as we've gotten a lot of interest already, as I said. And again, if folks on the call want to know more about the SolarAPP, you're welcome to email us at the link here, or again, check us out at solarapp.nrel.gov. Importantly, as I mentioned at the start of this, we are focused on residential rooftop PV systems as a phase 1. The next kind of frontier for us is what we're looking for going forward is to incorporate energy storage. So that'll be residential energy storage into the application. Right now, we're actively developing a set of what we're calling straw requirements of storage that we'll be vetting with code officials and jurisdictions going forward. So that'll be the next kind of tool that we put into the application, or not next, the next permit that we'll put in the application. Then we're also looking at things like incorporating commercial projects, as well as other elements of permitting, main panel upgrades, etc. And so that's where we are with the SolarAPP right now. Like I said before, if folks want more information about the application and what we're doing, you're welcome to email me or check us out at solarapp.nrel.gov, as I mentioned before. And yeah, I can end there and reserve any remaining time for our next speaker. And I look forward to answering any questions in the chat. Thanks so much for your time.
Excellent, Jeff. Thank you very much. Bill Cook does have a question for you in the Q&A, so we can queue it right up. But in the spirit of keeping things moving, we will move right on. Next up, we have Everett Barber, who will share with us his research on long-term PV performance of grid-tied systems. Can you load it up there, Everett?
Will do.
Greetings.
You see it?
We can see it.
Interim report.
Interim report.
Okay.
Take it away.
Since I don't have much time, I'm going to go along really fast, and hopefully there's enough information in the slides that someone can get in touch with me if they want in the Q&A session. So I've been at this since the early 70s, that is solar applications. They started with thermal applications, and then in the late 1980s, early 1990s, began to be involved also with solar electric applications. This is a long-term project that has interested me. It's I'm looking at the long-term degradation, as the title says, of grid-tied solar electric systems. My name on this is on the slide, and contact information if anyone wishes to reach me. just a second. The basis for the comparison that is going to come up shortly is any energy output of the solar electric systems, in kilowatt system, per kilowatt system capacity, and per unit collector area, square feet or square meter. This is a graph showing 18 systems that are all fixed mount working systems. I've had more systems, but have lost some for various reasons. And those above the line, that red line is the average for the output of all of those systems. And the characteristics of the systems are listed below. For example, on my spreadsheet, G indicates this system, the kilowatt capacity, 2.95. Are you able to see my mouse?
We can.
Okay. And then the number of years the system has been in the study, and then the type of cell that's included. So this one is on a per kilowatt basis. The next one, whoops, I'm sorry. The next one is on a same systems, same relationship to one another, and it just shows the output on a per square foot basis and a per square meter basis. This one is for one tracking and one single axis, I'm sorry, one fixed and one single axis tracking system, showing the output of the two, and that's a 10 years long set of data. This is for the PV watts based output of a fixed and a single axis tracking system. This shows the default parameters that are integrated with the software PV watts, which is a very useful tool for designers, which I'm sure you must be familiar with. And in 2010, they changed the default parameters to those shown here. It had quite an impact on the system output. The projected output via PV watts for a fixed array in selected cities is as shown by these different bars. The blue lines are for the pre-2010 defaults and the red for subsequent to 2010. Interesting to look at Berlin compared to New York or a number of other cities that are in the US. And yet the Germans have a significant amount of more solar activity than we do. This shows an interesting aspect of the using PV watts to determine the output for those systems. They've indicating that about plus or minus 5% variation from one city to the next in about 60% of the US. This shows a typical, the magenta colored lines are from the PV watt output, and the black colored lines are from the actual metered output. In all cases where I've had close output over the years, PV watts has been an extremely, a very useful and competitive tool. Tom, do I have more, how much time do I have?
Let me see, you have about 4 minutes.
Okay, proceeding. This is just for interest with PV watts. I found one of the system owners in my study had a gradual long-term deterioration of their system output. The company that was responsible for repairs to the system would not make the repairs until they saw the output in the orange icons, symbols, and then they repaired the system. It took that to get them to repair it. This is another system view, and it's the percent deterioration of projected of output projected at 20 years for those same 18 systems you saw above. And the deterioration is above the zero line, and a curious aspect of this is the gain, which is negative deterioration, is shown below, and it had to do with the use of the Excel trendline function, and the fact that there was a real dip at the start, the first year, from systems that had problems on startup, tree shade just being one of them. This is showing the trendline function and how a 14-year-old system varies over time. And this particular one goes to about a 35% reduction at the 20-year term. And this is just a table that shows the manner in which that reduction is calculated or projected over in this side. I'm about 4 slides from the end, Tom.
You're doing great.
For
Thanks,
system
Everett.
output deterioration. This is always interesting to most people, especially system owners. And this is on the slide, and if you want a copy of it, I'd be glad to provide the slides. And there are a few others that are also significant, but I chose not to list them, divorce being one of them. This is just showing what the efficiency of the collectors that were in the study. There are 28 systems. And this is the efficiency of those collectors when they're new. And this shows the manufacturers of the modules that are used in the systems in the studies. And the ones lined through are out of business. The red are a new owner. You may know that Sanyo was taken over or sold out to Panasonic down at the bottom. So much for that. There's another study that was of interest to me when I got started with this. These are NREL publications. In this case, an extensive review of the literature on module degradation. And then another study by Lawrence Berkeley Labs. And the last, oops, I'm not.
Uh-oh, you went to the end.
Michelle, what happened to, once by the end of it here?
Sorry.
While he's doing that, I will note that in the chat section under the participants list, there's a question for you, Gaylord. Go ahead, Everett.
Okay, this is the last slide. And this is should be of interest to anybody that's interested in solar electric and solar thermal. But on the left is the output in kilowatt hours AC per year per square foot for PV systems. This is from metered systems. And this is the output for solar medium temperature solar thermal systems. And this is from literature showing various researchers who've confirmed those data. So there's about a multiple of 4 more energy per square foot out of a solar medium temperature solar thermal system than out of a grid tied solar electric system. And that's it. Sorry if I ran over.
Oh, you're good, Everett. You're great. Again, we have a healthy participation on this, you know, really thumbs up to ACES. Everybody, thank you for joining. Amelia Amon is our final speaker in the PV technical, in the technical track. And Amelia, without any hesitation, please take over the screen and let's go.
Okay, thank you, Tom.
What do you have to
Welcome.
activate?
Okay,
You got it.
it's my second slide, but anyway, yeah, so Tom and I go way back to when I was, well, I still am an industrial designer, and I was interested in how I could make solar more accessible, more friendly, and more beautiful. And Tom at the time was head of NESI, and we ended up with the solar-powered ice cream cart, which sort of got me started. And so most of my work has been in off-grid products and in integrating solar into the environment, into the built environment, you know, and convincing the public that it can be more equitable, sustainable, and lead to a higher quality of life. So the aesthetics of energy. But as we've seen in many presentations during this conference, the economics right now are leading to these large-scale solar farms where you just have economies of scale. So the question is, can they be beautiful? Sorry. Well, what could be more beautiful than the abundance of nature? 75% of all fruits, nuts, and vegetables, so most flowering plants that we eat are pollinator dependent. In fact, even some of the beverages that we enjoy, this is a beer, a Minnesota beer made from local hops and honey that was sourced from a solar array, a pollinator-friendly solar array farm. And I'm sure that you've all heard that the United States or the whole world has a big problem with species declining. The bumblebee species have been declining by 46% since 1970. So this is an area where the industry can actually help. The other area is in caterpillars. Birds, butterflies, and beneficial insect populations are also in sharp decline. Birds by 29% since the 1970s. And much of that is due to habitat loss, and particularly native species. So invasive species and farmland, and obviously construction has taken over where a lot of birds would get their source of food. According to Doug Tallamy, professor of entomology and wildlife ecology at the University of Delaware, a single pair of breeding chickadees must find 6,000 to 9,000 caterpillars to rear one clutch of young. So it's a big task for a bird, and I really recommend this book by Tallamy or any of his books if you want to know more about native species and the importance. And then how important is community acceptance? NREL estimates that we're going to need 6 to 8 million acres of solar capacity to, you know, get to our goal of 100% electricity, 100% solar, or 100% renewables. And communities are not going to accept it if the land is barren and ugly. Here you see some farmers objecting to solar farms, and the sign says, if the rest, why the tree line if the rest is not an eyesore? And so, yeah, this is a big issue. And another amazing fact is that when they add pollinator species to solar farms, the outlying farmland is actually more productive, enough to make up for the land that is taken by solar. So it's a win-win for farmers and communities. And also for developers who want to bring in this added benefit, because, you know, they'll have the competitive advantage with corporations, universities, rural electric co-ops, and electric utilities. So all of those people are looking for the pollinator solar. Another thing is with increasing climate change, the deep roots of native forbs and grasses will sequester a lot more carbon. We just had a presentation on dust. The plants will also stop erosion, much more so than turf grass, which only the roots only go 3 to 6 inches, and amazingly more so than gravel, which creates a heat island effect. It also is a lot better for flood because it absorbs groundwater. Another amazing fact is that the plants themselves can cool the panels by cooling transpiration. They keep the ground around it cool, and NREL has seen that at every degree above 77 degrees, panels lose about 0.6 of efficiency. So in studies that have done, and this also works on solar roofs, combining solar roofs with green roofs, you can actually get 2% more efficiency out of the panels by using native species. And for more information on this, I recommend the Center for Pollinators and Energy, beeslovesolar.org, who provided this chart. And if you really want to make your solar thing more productive, you can add grazing animals seasonally, so that you not only get sorry about the dog. He only barks when I'm presenting.
He's chasing the sheep around.
Right, he's chasing. He heard sheep, and that was that. Right. Okay, but with all these benefits, what are the costs? So this is a chart by Virginia.gov. And so you see that it's like when you're building an ecological or a well-insulated house, you're paying more up front, but over time, your costs are going to go way down compared to the maintenance costs for mowing turf grass. And so you see between years 3 and 8 are basically your break-even point, depending on what kind of grasses you use and how much you spend in the development section. But by year 20, you're using half the maintenance of operation and maintenance costs. So actually, I'm a little ahead of myself because I sort of rushed through the beginning. But so I guess the next question is, who all is doing this? So already in 8 states out of the union, this pollinator species solar scorecard is part of our legal system, part of the law. And in 5 other states are looking at it for procurement and for county ordinances. So, and then the rest of the country, there is a national pollinator friendly scorecard. And the pollinator friendly scorecard, it works very much like a sort of like a LEED thing, where you get points for different aspects of what makes it a pollinator friendly solar farm. And these aspects are vetted by the entomologists, local entomologists from each state. So it comes down to percentage of wildflowers, percentage of native species, the number of species that you have available, the nearby assets, is it helping other farms in the vicinity, a management plan. A lot of times these plants have a succession, and do you have a plan for that? And another advantage is that after the 25-year leasing period, the land can go completely back to organics, so any organic usage. Adequate signage is also important, and is there any local insecticide risks? It's not about replacing every blade of grass with a flower. It's a tool to demonstrate that project has implemented incremental change in seed mix design to accomplish a meaningful result. And that's from Rob Davis, who, again, I recommend that website, beeslovesolar.org. So back to my mission on the aesthetics of energy. When I'm working on a problem, I never think about beauty, but when I have finished, if the solution is not beautiful, I know it is wrong. That's our Buckminster Fuller. So there's my information. I'd like to get any questions in the chat room, and thank you for your time.
Beautiful in every way, Amelia. A great way to end a
Thank you.
great session. Really appreciate it. You do have a question from MDL-LCC, and I note that MDL-LCC, you also put that question to Gaylord in the chat box, so hopefully everybody got in. We are at the end of the session. I want to thank everyone for joining. Please continue the dialogue in the chat room. And please get to the next session. Hooray again for ACES. Thanks everyone for participating. Have a
Thank you,
great
Tom.
day. Bye.
Thank you,
Bye,
Tom.
everyone.
Thank you.
Bye.
Thank you, Tom.
Thank you.
Bye, thanks.
Thank you. Bye.